scheme theory, I think I will skip some maybe definition of shifts, but I will define some basic scheme theory things, and then I will talk about my main object, which is Hilbert scheme. Then I will come into Hilbert-Chow morphism, which is a morphism to study the properties of Hilbert scheme. And finally, I will go into cohomology of Hilbert scheme, but actually this part I haven't touched it yet. It's just I will show some main theory and main theorem and what I will do next semester. And first, let's see some basic definition of scheme theory. This is basically I study the book of Harshang's algebraic geometry. And first, I define a direct image sheaf. And we know that sheaf is a contravariant functor from the category of open set to a category of group or ring. And we define the direct image sheaf from a function of continuous map of topological space, and we define the direct image sheaf f star f on y by f star f v equals to f minus 1 v for every open set v in y. And then we define what is a ring space, because later when we define a scheme, we define its morphism and isomorphism by this morphism of ring space. And basically, I'll skip 1, 2, 3, and the main part is what is a local homomorphism. It is a homomorphism between two local rings with maximal idea MA and MB, and it is a local homomorphism if phi inverse of MB is equals to MA. And we define a morphism of locally ringed space as a morphism of ringed space such that the map of local rings F sharp P, this P means stock from the OYFP to OXP is a local homomorphism of local rings. And then we come to what is a scheme. Actually, first we need to define an affine scheme. It is a locally ringed space which is isomorphic to the spectrum of some ring. It means that give a ring its spectrum is spec A is contain all of its prime ideas, and we define a scheme as a locally ringed space such that every point has an open neighborhood such that the topological space U together with the restrict sheaf, it's just the sheaf on OX restrict to this open set. It is a affine scheme. And then we come to some morphism, because when we're studying category, first we define the objects, then we define the morphism. And the morphism of the schemes is morphism as locally ringed spaces, as we just defined earlier. And from this, we actually use a theorem that I haven't said, but we will use it later, is that the global section, which means the sheaf apply on the whole space of a spectrum of a ring. For example, the spectrum of R, its global section is isomorphic to the ring R. We will use this property later. And then we need to use closed subschemes. First, we define a closed inversion. It is just a morphism of schemes, and this map is defined on its topological space, which is SPY, and then furthermore, we have an induced map F sharp, which is from OX to F star OY of sheaves on X. And we ask it for B surjective. And we define a closed subscheme to be an equivalent class of the closed immersions. And we define it as a closed immersion because sometimes even if two subschemes of scheme X have the same topological structure, but their sheaf may be different. For example, the spectrum of Kx quotient X and the spectrum quotient by the idea generated by X squared, they have the same topological space, and the topological space are both closed set of the whole topological space, but they have different structures, so they are different closed subschemes. And then we define what is a separated scheme. We define it by the diagonal morphism, which is the unique morphism of the diagonal map of stand X to the X fiber product with X. Sorry, I think I need to close the sound first. Okay, the diagonal morphism. Then from the diagonal morphism, we have two projection maps, P1 and P2. And we said that the morphism is separated if the diagonal morphism is a closed immersion that we defined earlier. And we also said X is separated over Y. And a scheme X is separated if it is separated over spec Z, because actually every scheme has a natural morphism to the spec Z. This is because that for every ring, we have a morphism, homomorphism from Z to the ring, and the spectrum is a contravariant functor. So we have a map from the spec R to spec Z, and after that we glue it so it becomes a scheme. And then we define a proper scheme. It is separated and of finite type and universally closed scheme. And the universally closed is just a version of closed that it is invariant of the closed property under the extension, base extension. It means that we change the base. And finally, we define what is a projective scheme. It is from a projective n space PAN, which defined as the proj of the polynomial ring. And we do the fiber product with projective space Y and as the projective n space over Y. And then we say that a morphism is projective if it factors into a closed immersion for some n followed by the projection. And a morphism is called quasi-projective if it factors into an open immersion followed by a projective morphism. Actually, we define the projective and the quasi-projective scheme here is because later when we define Hilbert scheme, we start from a projective or quasi-projective scheme. And so let's come into our second part, which is the Hilbert scheme. And first, let's review some category theory. If C is a category, we define its opposite category to be the category with the same object, but the morphism, we change the direction. And we define a covariant functor is representable if it exists A in the object such that this functor f is isomorphic to Hom C of A, this functor. And then let's define what is a Hilbert functor. First, for an S scheme, which means that X is a scheme and there is a morphism from X to S. And then we define a set Hilbert X over S as the closed subschemes of X such that this map is proper, flat, and of finite presentation. The proper we just defined earlier, and the flat we haven't defined, but I just here to explain that flat is to makes the fiber, which means the pre-image of a point of this scheme, of this map to be to have some property like the Hilbert polynomial or the dimension and the number of points. These things are these things to make it invariant when we change the scheme. And then let S be an S scheme. We define the Hilbert functors that is a functor that send every scheme T over S to the category of set, which is the set we defined earlier. And this remark shows that this map is actually a functor because the fiber product induced this map. And then let's define a Hilbert scheme. We just define what is a representing functor. And for this Hilbert functor, Gross and Dick have shown that this functor is representable. And we call this representable functor is called the Hilbert scheme. And we have the property that all of its connected components are quasi-projective. And we notice that in here, we also ask for S to be Noetherian because if S is a not Noetherian scheme, actually there are some counter-examples that this functor is not representable. And then we come into Hilbert scheme of n points. This is actually just a subfunctor of the whole Hilbert functor because the whole Hilbert functor and the Hilbert scheme is quite large, and we just think of some part of it. And actually, this classification is by we choosing different Hilbert polynomials. But here we just talk about endpoints, which means that the Hilbert polynomial is just a constant. It only has value on 0. So we define this Hilbert n also x over st is equals to the closed subscheme in the whole Hilbert set, and it is finite locally free of rank n. We find that this finite locally free of rank n, we can define this because we ask for the map to be flat. After we ask for this, we can have this property that it has rank n because it is an invariant invariant thing, and then we have the theorem. We just say that the whole Hilbert functor can be represented by a very large Hilbert scheme, and here we just consider the Hilbert scheme of n points. It is just here we use this surjective map to mean the closed subschemes of X, and actually this here we there is an I star here should be, and we just ignore it and write it as like this. But the I is the inclusion map from Z to X, and we ask for its dimension of global section to be n. Here we just consider the X to be the spectrum of algebraically closed field like K, like we can choose complex number like C. And actually, these two things are related because we are right locally free of rank n here, and it will relate to the dimension of the global section. Because the locally free just of rank n means that if we restrict the shift to an open set, and it will isomorphic to the shift on this open set to the power of n, and here we just choose our S to be spec K, so all of its open set is just U. So we can just because spec K only consider contain one point, so the open set is the whole space if we ignore the empty set. And after that, we just want our shift on the whole space to isomorphic to the OU to the power of n, which means O spec K to the power of n. So, and we apply the global section on the both sides, we get that the global section of the shift has dimension n. And we call this the Hilbert scheme of n points. Then follow from this, we can define a definition called length, means that a length n subscheme of X is a finite subscheme Y such that the K vector space gamma, which means the global section of this subscheme has dimension n. And from this, we can see an example of the Hilbert scheme of n points. We just consider our scheme to be AKD. And this is the spectrum of the polynomial ring. And we have the Hilbert scheme of n points of AKD is equals to the idea in the polynomial ring such that the dimension of the whole polynomial ring quotient this idea is equals to n. And this follows from the correspondence below that the point of the Hilbert scheme is correspond to the less enclosed subscheme of the scheme and correspond to the ideas I in the polynomial ring such that the dimension of the polynomial ring quotient this idea is n. The first correspondence following from the theorem on the last page, and the second correspondence is that every closed subscheme of the affine scheme is of the form spectrum of the polynomial ring quotient an idea, and so this has a unique correspondence with an idea of the polynomial ring. And we can see a more specific example that Hilbert's scheme of n points of A1 is isomorphic to AN. This is because that by the last page, we ask for the dimension of the Kx quotient I is equals to n. And we know that Kx is a PID. So every idea must be principal and it is generated by a polynomial with degree n. And so this will correspond to a point in the affine scheme. And then let's introduce what is a Hilbert-Chow morphism. Actually, this is a morphism that we try to study the Hilbert scheme, and we finally see that the Hilbert scheme is a resolution of singularity of the symmetry product. First, let's define what is a symmetry product. The symmetry product for a set is defined by the xn quotient the Sn. We just take its orbit. And then we can define a quotient topology on it. And we define the locus to be the points in the symmetry product that every point is different. We can see that the U is an open set in this symmetry product because the symmetry product topology is the Zariski topology with the quotient topology. And then we can define the Hilbert homomorphism as a map from the Hilbert scheme to the symmetry product that sends every closed subscheme to the sum of the formal sum of the points in X with the coefficient, the dimension of the stock of this closed subscheme on these points. And we define the smooth locus as the pre-image of the U that we defined earlier. And then we come into the main theory is Fogarty's theorem. It says that the Hilbert scheme X, when the X is a projective scheme, which means that it has dimension 2. It is non-singular and has dimension 2n. And the pi we defined earlier is a resolution of singularity. And the proof, I haven't very finished every detail, but the main idea is that the Hilbert scheme's tangent space is home of IZ to OX quotient IZ, and we use the chain short exact sequence to form a long exact sequence and use this to conclude that the dimension is invariant. And we know that sheaf is also a abelian category like group and rings. So the short exact sequence and the long exact sequence things is just the same as we learn it in algebraic topology. And later that we use some duality theorem that I haven't come into this part, and we conclude that there are many terms are zero in this long exact sequence. And then we finally can conclude that the dimension is equals to n. And finally, the last part, in the next semester, I will comes from where conjectures and use these conjectures, which has already proved to prove the Goldschag's formula. This is the last things I want to achieve, which is the Betti number of the Hilbert scheme. We have this formula. Okay, that is my presentation, and thank you.
Okay, thank you. I think we have short of time, so we still have 3 minutes. Maybe Dulit can ask some questions.
I actually have no technical questions. I have like one thing I like to, I'm out of very curiosity actually. So how did you learn all of that? Did you take algebra geometry with Yichen before that? Or?
I took classical algebraic geometry with Yichen earlier, and the modern part, which contains a scheme theory, I learned it myself this semester.
Which reference did you follow? I think you mentioned, I forgot. Like, was it Harshon or?
Yeah, Harshon.
Only Harshon.
I just read the Harshon chapter 2 from, I think, mainly the first 5 section.
Okay, so you did not refer any other textbooks?
Actually, I sometimes reading there's a red books. I forget the
red
right.
book by Mumford.
I think not. Can you wait for some seconds? I check.
Oh no. Just I mean, you know, it's very nice actually. Like,
yeah, I think he discussed with Chiwi as well.
Yeah, this book.
Remember Chiwi?
Okay, I mean, excellent actually. Yeah.
High course. This one.
Okay.
Yeah.
Excellent. I mean, so yeah. So
yeah, they do discussion with Chiwi, the master students. Yeah. Muni,
okay.
Yeah.
Okay.
Yeah. They have like a weekly discussion.
Okay, because you know, I mean, with the 10 weeks, technically you have like a 12 weeks, right, for like final year project, like in a semester, right? Like it's a great. I mean, like I'm very surprised to see, like, yeah, it's well organized. The slides, you know, I mean,
okay, thank you.
You put some examples to justify, like, you know, I mean, you understood the things. I mean, that is great, actually. Yeah.
Yeah.
So excellent. So yeah, just please continue and, you know, do some good work.
Okay. Thank you.
Okay. All right. Good luck.
And that's all. Thank you, Dulip, and thank you, Eric.
Thank you, Yichen. Thank you,
Alright.
Julie.
Yeah.
Okay, see you.
Good luck. See you.
I can leave now, right?
Yeah, I mean,
Yeah.
it's up to you, but I mean.